Welcome back. This is the third part of the presentation, and we will be looking at human performance and the ketogenic diet. So will it work? Is this diet compatible? Will the ketogenic diet suffice when it comes to rigorous training and elite competition? In the next slides, this is what we will discuss. So up first is a table, and this table represents the current recommendations for athletes, and real simply, the only thing that really differs here is the calorie content based on gender, but as you can see, other than that, it's all the same. And so 5.2 grams per kilogram of carbohydrates is quite a bit of carbohydrates per day. So if you have a 100 kilogram individual, we're looking at about 520 grams of carbohydrates per day, which is roughly going to equal 2,000 calories coming directly from the carbohydrates. This is in stark contrast to the ketogenic diet because obviously carbohydrate is the main constituent of the caloric intake. And this intake is actually common in athletes like Kenyan long distance runners and Tour de France cyclists. So why is such a high daily intake of carbohydrates recommended for athletic performance? Do these recommendations parallel the dietary patterns seen in human evolution? After all, didn't prehistoric humans have to quote-unquote perform under varied conditions and be successful in their progression to become the modern-day Homo sapien? We will see in the next slides the summary of human dietary history and explore the possible reasons carbohydrates are recommended in such high amounts. So when we look at human evolution and we look at the dietary patterns seen throughout this time, we have to start about 50 million years ago. And this is the time period shortly after the end of the dinosaur reign of the Earth. And it's thought to be through fossil evidence and other archaeological and paleontological evidence that we consumed more or less an insect-based diet, going on to more of a fruit-based diet, to a plant diet, and then the plant diet maintained for quite some time, and then we see that flesh foods become of some importance, but the plant-based and the fruit-based diet are still the main components. Thereafter, still another 2.5 million years or so, the hunter-gatherers start to emerge, so more meat now is being consumed, and this is where the most meat actually will be consumed throughout this time period, throughout this timetable, and eventually the diets begin to alternate, and this may have been due to changes in the environment. And so intermittent consumption may have been the common dietary pattern about 900,000 years ago. Then hunting becomes more of a staple to bridge the gaps between seasons, and storage of nuts and bulbs and tubers becomes common during this time. And eventually, around 400,000 years ago, an omnivorous diet becomes more commonplace in present-day China. And we see here that they have meats, wild fruit and berries, shoots and tubers, birds and their eggs, insects, reptiles, rats, and large animals are all a part of their diet. And so it seems that the omnivorous diet is just a combination of all of the previous historical diets. And so from that time, we see more seafood being eaten and more variation throughout the diets overall. And the most recent time period on this timetable, roughly 40,000 to 10,000 years ago, we see subsistence in Europe is provided primarily by hunter-gatherers, where at least 50% of food is meat. And we also start to see that grain harvesting begins and flour is made within the region of present-day Israel. We saw that the insectivorous diet was very common in the earliest times. So what is an insectivore? It's an insect-eating carnivore. And a carnivore is considered to be an organism that derives its mainstay of energy from animal tissue via predation or scavenging. So this fits right along with what we saw later in the timetable. However, if you eat insects, you are still considered a carnivore. An insect may not have flesh like animals that we consume on a regular basis in modern times. It's still considered to be a carnivorous dieting pattern. And up to 80% of the world still practice insect eating, called entomophagy. This insect eating actually includes their eggs, larvae, and pupae. So they're not just eating the insects that you see crawling around, they're also eating the insects before they even become insects. Nutritional content of insects is available, and that link right there that is beside this bullet will bring you to a video that talks about eating insects and the stigma that goes along with it. So the major macronutrients of insects are pretty much what you see in the ketogenic diet: proteins and fats. And we see here that there are significant quantities of specific kinds of fatty acids, and they're very healthful. And also we mentioned that limiting saturated fatty acids is a very good thing, especially while on the ketogenic diet. And this fits in quite well too, because the amount of saturated fat within insects is nearly non-existent. Also, insects contain very high levels of phosphorus. Nearly 100% of that phosphorus is bioavailable, meaning it can be readily absorbed and utilized. And compared to plants, I mean, it's a disparate comparison. 30% for plants. Insects also have a substantial amount of magnesium, sodium, potassium, chloride, iron, zinc, copper, manganese, and selenium. And we discussed a little bit about the ion of potassium earlier, as well as magnesium. And the magnesium was linked to possible exacerbation or as an aggravating factor with oxygen toxicity seizures. Copper, we saw it plays a great role within regulating oxidative stress, and selenium, which we saw if there is a deficiency of selenium, it can also be an aggravating factor in oxygen toxicity seizures. Finally, all insects are relatively good sources of B vitamins and contain modest amounts of vitamins A and E. So this is quite helpful as well, since while on a ketogenic diet, the consumption of carbohydrates is very minimal. So the intake of the typical B vitamin rich food, grains, they are not consumed. And so insects may be an alternate source of B vitamins while on a ketogenic diet. So as we saw after the insectivorous diet, there was a frugivorous diet. So what is a frugivore? It's a fruit-eating herbivore. So what is an herbivore? And so this is an organism that derives the majority of its energy from plants. And specifically, we need to mention a folivore, and this is an herbivore that gets most of its energy from leafy plants and shoots. And since we are primates, that's why I had to include the concept of folivore. If we look at the folivore's ability to break down plant material, it's relatively decreased compared to that of a true herbivore. There's evolutionary concepts that relate to the increased length of the gastrointestinal tract and also the symbiotic bacterial colonization that hints toward the possibility for these differences in the gastrointestinal tract. Immature leaves are consumed rather than mature ones, and the reason this is so is because greater amounts of protein and usable energy are found within the immature leaves, and it's also relatively lower in fiber, still high in fiber, but relatively lower in fiber. And because the higher the fiber, the more nutrients that may be lost. Although frugivorous primates mainly consume fruits, their diets are still supplemented with insects and leafy plants. And we look to see the nutritional content of fruits, which are typically high in water and carbohydrate and low in protein and fat. And it makes sense that the frugivores, especially the primate frugivores, will supplement their diets with the insects and leafy plants because of the low protein content and also the low fat content. Realistically, if you're going to be eating plants and fruits, there's a high probability that there's an insect that's going to make its way into your mouth. So it makes sense that frugivorous primates supplement their diets with insects. This right here looks like pretty much all the foods we could ever want to really eat, especially in modern times. So an omnivore is an organism that can get its energy from many sources, including plants, animals, algae, fungi, and bacteria. So omnivores are typically opportunistic, meaning that they're going to take what is available and they're going to make do with what is available. And so it's essentially being adaptable to the environmental factors or pressures. So when seasons change, they're able to start hunting or start grazing, or depending on what kind of animal they are, if they are omnivorous, like bears and humans. So the omnivorous diet, especially in humans, is well adapted and well suited for nomadic lifestyles. So the omnivorous diet essentially enabled the spread and the growth of human population throughout the globe. And as we kind of mentioned earlier in the timetable algorithm, the omnivorous diet is seemingly the result of a culmination of adaptations for enhanced survival. You're probably wondering, what is the point of all this? Why are we talking about the evolutionary history in a presentation about human performance in the ketogenic diet? Well, for one thing, the changes in dietary patterns highlight the adaptability of our ancestors and the potential for these same adaptable genes to be found within present-day humans. But the main fitting piece here is the fact that these diets provided the sustenance for performance, which afforded survival throughout evolutionary history. Even low carbohydrate intakes have enabled success. Based on the overall look at the dietary changes seen in human evolution, and noting from the ketogenic diet section of this presentation the fact that glycogen never becomes entirely depleted, we most likely would think that carbohydrates are important, especially since for the entire period of 50 million years ago to present day, there is and has been at least some carbohydrate consumption. So you might ask, is this why our bodies manufacture glucose from proteins, or why fats are the preferred energy source while at rest and during endurance type physical exertion? I don't know. These questions may be more recognizably phenomenal than scientifically provable. However, there are geologic periods that point to climatic and subsequent environmental change. And it may have been these changes that forced certain populations, for example, like northern populations, to adapt. And through such adaptive forces came dietary and nutritional adaptation. The ketogenic diet and other similar diets like the paleo diet may in fact be more closely related to a hunter-gatherer type diet, even though they may not apply to every dietary variation in human history. They do more closely represent the basis of dietary patterns seen throughout human evolution. Feast and famine cycles are common to the animal kingdom, making us adaptable in such situations. Ultimately, the relinquished intake of refined carbohydrates and starchy foods could help promote an increased intake of fibrous fruit and plant foods. And this is compatible with the ketogenic diet and most likely also human performance. So this slide essentially continues from the last slide and displays why the current recommendations might exist. Essentially, agriculture brought about refined grains and sugars that outshined fibrous, leafy, and cruciferous plant foods. Although sugar production was mainly confined to India until a few hundred years ago, sugarcane agriculture has become the world's largest crop by production quantity. So if we use this time lapse and compare it against times before agricultural revolution, we will see how the diets have generally differed. But first, look at the prevailing studies that came about because of the rise of agriculture. So a Danish study in 1939 looked at how low, moderate, and high carbohydrate diets would affect endurance time to exhaustion. And in short, high carbohydrate diets were the ones that tested most favorably. If we look at a study during World War II, a pemmican study done, where they used pemmican without carbohydrates, and when the soldiers were eating this pemmican, it only took 3 days for the experimenters to realize that this was not going to work because the soldiers were not able to accomplish their tasks. So the pemmican study only lasted for 3 days because of this. Lastly, in the 1960s, the percutaneous needle biopsy was developed, which enabled people to figure out what the major fuel was for vigorous exercise. Well, at least it led them to believe that they knew what that fuel was. And muscle glycogen became known as the limiting fuel for high intensity exercise and the basis of the strategy of carbohydrate loading. And if we look at these first two studies, the Danish study and the pemmican study, we see that the Danish study only lasted for 1 week and the pemmican study only lasted 3 days. So keep that in mind. The Paleolithic era, along with the diet, was described 2 slides ago, showing the evolution and variation of human diets. The Neolithic era began as the inception of agriculture occurred. As this table provides a basic comparison of the 2 eras, we can see that the Neolithic diet, which is based on agricultural standards, provides nearly all its caloric intake from plants. If we compare this source of intake with the table of showing recommendations for athletes, then it is likely that to achieve 70% of calories from carbohydrates, one would likely have to consume an amount of plant food similar to that of the Neolithic diet. So where did we go wrong? Was it due to the agricultural revolution? Do we fancy carbohydrates over fat because of this uprising? So carbohydrates may be fancied over fats because there may have been aspects of a high-fat diet that were not considered. So what was not considered? Possibly the keto adaptation timetable. the provision and optimization of sodium and potassium may not have been adequate in these studies looking at high-fat diets. Enough protein may not have been supplied throughout the high-fat diet application. And understanding the special instances when carbohydrates are necessary for anaerobic performance may not have been considered, or conclusions may have been drawn without understanding the difference in performance types. So let's look at keto adaptation real quickly. It's a 3 to 4 week timetable until adaptation completes, as we saw before. And we also mentioned that it's the full adaptation to nitrogen, fat, and carbohydrate metabolism. And we must mention that exercise tolerance depends on this timetable. So the exercise tolerance is going to change within the first 3 to 4 weeks. So where do people go wrong when they're on a KD? Well, adhering to carbohydrate restriction is not the easiest thing to do. So people who have reported exercise intolerance while on a KD, they have also reported cheating or not being able to adhere to the carbohydrate restriction. And also, people on a KD typically are restricting their calories compared to before the KD, so this also makes exercise difficult. On to the second point. The short-term need of these two ions is quite clear. And the long-term need is quite clear as well. And so we need it for cardiovascular reserve and also the preservation of body mass and function. Why aren't sodium and potassium provided while on a KD? Well, many people that cook or boil their meat discard the broth, so a lot of the potassium and sodium within the meat is going to be cooked off. So it would be advantageous to not discard the broth. Baking, roasting, and broiling meat will cause loss of potassium, and also the limitation of fruits and vegetables that are high in potassium typically are not consumed while on a KD. So we're going to look at how these ions affect exercise, and these ions enable a normal amount of blood volume, which also allows for adequate vasodilation, meaning increased blood flow during exercise. And they effect optimized nitrogen balance and functional tissue preservation. So they are associated with protein metabolism. So why is sodium important? Well, sodium allows for the maintenance of water balance, the absorption of glucose and amino acids, and regulation of muscle and nerve function. With increased sodium, there's typically increased calcium loss in the urine. Long duration activity necessitates sodium addition to fluids, so prolonged exercise is going to demand sodium addition to the fluids during the rehydration period. With sodium loss, there's cramping, especially in hot environments. The intensity and duration of the exercise will dictate the amount of sodium loss. When plasma levels drop below 130 milliequivalents per liter, seizures may develop, lethargy and loss of unconsciousness may occur, and also exercise-induced hyponatremia, where this is where you lose sodium and essentially your blood becomes very diluted. So this is another reason why it is important to include sodium within the fluids during rehydration. And in people who are working out that typically drink a lot of water, depending on the intensity and also the sweat rate of the individual, they may be losing less fluid than they're consuming. So that can also cause the hyponatremia. So potassium, why is potassium important? Well, potassium aids in the promotion of cellular growth, the maintenance of body fluids, the generation of electrical impulses in nerves, muscles, and heart, and regulation of acid-base balance. And if you were wondering, the amount of potassium relates to muscle mass and glycogen storage. So optimizing the potassium will allow for an increased muscle mass as well as glycogen storage. So even though you're on a low carbohydrate diet with the ketogenic diet, you still are going to have glycogen storage. So it might be beneficial to maintain an adequate potassium intake. Increased potassium will decrease calcium and increase excess sodium and water loss in urine. So we saw that increased sodium causes decreased calcium, but with increased potassium, there's decreased calcium release in the urine. This is a good thing, so that if we balance our potassium and sodium intakes by improving our potassium intake, we can mitigate the changes that may occur with sodium intake, which is the loss of calcium. So with high and low potassium intake and blood concentration, there can be effects to the heart, which are not good at all. So that's another reason why potassium needs to be optimized. And so potassium loss is related to skeletal muscle fatigue. So with performance aspects of a ketogenic diet, if potassium is not optimized, this could lead to muscle fatigue, which would definitely cause exercise intolerance. And thankfully, not much potassium is lost in sweat. Sources of potassium include pork loin, halibut, rainbow trout, clams, cod, tuna, sweet potato, and bananas. Obviously, there are other foods that contain potassium, but these are ones that might be consumed on a ketogenic diet, bar the sweet potato and banana. So what about the protein intake? Why is that important? Well, 1.2 to 1.7 grams per kilogram of protein is necessary. And this is so to maintain functional tissue. And when you maintain functional tissue, then you maintain your VO2 max. But if you don't take enough protein, you can lose functional tissue along with the VO2 max. On the other hand, if you take too much protein, greater than 25% of your total calories, this may suppress ketogenesis, thereby dismantling the beneficial adaptation to ketone bodies. And what happens is, if you increase your intake of protein, you may be supplying the body with glucogenic amino acids, and this could be the carbon backbones to start up gluconeogenesis. So what's the overall or general consensus of a KD in exercise? Well, the KD has been found to be able to maintain functional tissues like skeletal muscle, red blood cell mass, and the heart and lungs. So the KD affords submaximal endurance performance and peak aerobic power, which is 60 to 70% VO2 max. We saw very early on in the presentation that the KD will spare muscle tissue through ketone body production, which will essentially spare functional tissue, and this will lead to maintenance of a VO2 max. So what's the downside of a KD in exercise? Well, the keto adaptation phase is the major downside, because people who are currently in this phase and they still are trying to work out may experience exercise intolerance, which is very discouraging. And based on their dietary discipline, meaning can they adhere to the carbohydrate restriction, their exercise intolerance may be indefinite because of them cheating. And anaerobic performance may be limited with the ketogenic diet because of the very minimal intake of carbohydrates. Well, this leads us to understand why anaerobic performance is limited. And so we just mentioned that due to the low intake of carbohydrates, there will be low muscle glycogen levels. And since anaerobic performance is primarily undertaken by type 2 skeletal muscle fibers, these muscle fibers typically generate their energy through anaerobic means. And we will be discussing fiber types in just a bit. So, knowing this fact, this actually discourages its use in many competitive situations that require a mix of both anaerobic and aerobic respiration. So is there a solution? Well, for fit individuals who begin the ketogenic diet, they may find that their exercise performance falls flat as compared to a non-ketogenic diet. So slight modifications are recommended in this scenario. The cyclical KD is where there is a carb loading portion during 2 days of the week, followed by low carb ketogenic diet for the remainder of the week. On the other hand, there's another option, the targeted KD. This modification allows the dieter to consume carbs before and after workouts and then consume a normal KD at all other times. If the goal is to lose weight or maximize fat utilization, then the cyclical KD may be the best option. Conversely, if high intensity, short duration exercise is the goal, then the targeted KD may be more beneficial. So let's get back to the basics. Fats are the primary source of energy at rest. They're also the primary fuel source during endurance exercise events. But don't forget, carbohydrates are still being used. So what does this tell us? The body is very well equipped for using fat as an energy source. And fat can be mobilized from the following sites for energy provision: intramuscular fat stores, adipose tissue, blood lipoproteins, and ingested fat during exercise. A KD will provide fats as well as ketone bodies for energy, but the proportion of fat and ketone usage versus carbohydrate usage during exercise is dependent on several factors. Because carbs and fats are oxidized simultaneously during exercise, the proportion of energy derived from each substrate is dependent on these factors. So what are these factors? The overall diet, the fitness level, the ability to utilize and mobilize fats, the availability of intramuscular fat reserves, which also depend on fitness level, diurnal training times, and dietary fat intake. The availability of glycogen reserves. This is dependent on intensity and duration of exercise and dietary carbohydrate intake. The meal consumed prior to exercise. The duration, short versus long. Intensity, the %1 rep max and or VO2 max. And type of exercise, anaerobic versus aerobic exercise. And lastly, energy type fed during exercise is another factor. We just mentioned factors that will affect the utilization of substrates. And one of those factors was how fat can be utilized. And so there are factors that affect fat utilization. And here's a list of them right here. But the major factor that it really comes down to is glucose availability. And so the availability of glucose may be the major determining factor, as well as genetic variations that either enhances or diminishes the effects of these processes. So the ketogenic diet will help with fat utilization because of carbohydrate restriction and increased storage of intramuscular fat. And we will see why in just a moment. So let's talk a little bit more about intramuscular fat. The advantage of these fats is that they're closer to the mitochondria, which allows for more rapid oxidation and energy production. The disadvantage, though, may be that they're only beneficial in aerobic events. The higher the intensity of the exercise, the smaller amount of fat used for energy. And aerobic events typically fall into a VO2 max range that has been shown to utilize energy derived in greater quantities from fat. Now, with elite athletes, their VO2 max may be very high, like 80 to 90% VO2 max, until they switch to anaerobic energy usage. But for most individuals, a 50 to 70% VO2 max will eat up the most fat for energy. So the storage of fat depends on some things, like muscle fiber type. And so a ketogenic diet could potentially increase the amount of intramuscular fat storage, more so in the aerobically inclined type 1 fibers. In a moment, we will see how a ketogenic diet may limit training options. Also, nutritional status can affect how much fat is stored intramuscularly, and exercise type and timing. So different exercise types can recruit different fiber types, which can lead to differences in oxidation rates. And so relatively higher intensity exercise generally uses more intramuscular fat. So what about those fiber types? Type 1, also termed slow oxidative, are types that are going to oxidize fat more readily, and they also have increased fat storage and also a greater number of mitochondria compared to other fiber types. However, their glycogen stores are low, and they're adaptable in such a way that they become faster for the specific training type. Type 2A, also termed fast oxidative glycolytic, are fiber types that can be adapted for training style. And so depending on the kind of training that a person does, the function of these fibers will follow suit. Storage of fat and glycogen, though, depend on the training type, but typically glycogen is high. So type 2B, fast glycolytic, are not going to oxidize fat as readily as type 1 due to the fact that they don't store as much fat, and also the number of their mitochondria is low. However, they do have high glycogen stores, which allows for anaerobic performance, and muscle hypertrophy is the greatest with this fiber type, which results from high intensity resistance training, which is anaerobic training. Ultimately, fiber types and their distribution and metabolic characteristics definitely play a role in how well a person is suited for a ketogenic diet and related exercise training. It seems with all this talk about training, fiber types, and diet, there has to be a major theme for how a ketogenic diet might affect human performance. So in general, what happens while consuming a high-fat diet? In the short term, there is an increase in free fatty acid use during rest and also an increased fatty acid uptake in exercising muscle. In long-term high-fat diets, though, there may be induction of adaptation within the muscle that enables increased oxidation of fat. The effective diet has an effect similar to that of exercise. What you eat will be what you burn, so eating more fats will jumpstart fat metabolism, just like endurance training will increase utilization of fats. This mirrors the concept of keto adaptation, showing how the body will adapt to what we feed it and what we do with it. More efficient use of oxygen is thought to occur, which corresponds with a fatty diet and relates to a 25% increase in energy usage in the heart while on a ketogenic diet like we saw earlier. And this may be related to the decreased respiratory exchange ratio, which leads to an increased time to exhaustion. So in general, what happens with exercise? Well, mitochondrial density increases, the enzymatic capacity of mitochondria increases, increased acyl-CoA synthetase is found in muscle, and this enzyme is used for activating fatty acids for their entry into mitochondria for beta oxidation. Storage of fat and usage in muscle increases. One study showed that 65% VO2 max correlated with 26% of derived energy from intramuscular stores. Overall, exercise is thought to induce adaptation, whereby intramuscular fat use during exercise increases and glycogen use decreases. This highlights how fitness level determines the primary energy source during exercise. Increased fatty acid uptake occurs in muscle. Increased capillary density in muscle and adipose tissue occurs, likely for the transport and utilization of fats. Increased oxygen delivery for fat oxidation occurs as well. Maximal level of fat oxidation is thought to occur around 60 to 68% VO2 max. And this type of training will lead to sparing of glycogen stores, which will allow for prolonged, high-intensity events lasting longer than 90 minutes. An example would be the last burst of energy at the finish line of an ultramarathon. The glycogen needed for that anaerobic explosion will be readily available because of this fact. And do not forget that monocarboxylate transporters are responsible for moving ketone bodies into the cell from extracellular compartments. These also increase with exercise. Let's keep in mind that genetic variability exists, which results in a mosaic distribution of fiber types within certain muscle groups, differing from person to person. This variability ostensibly results in invariable differences of exercise and fitness outcomes. Simply because a person runs and runs to their heart's content does not mean he or she will be the runner that they're striving to become. The existing genetic variations are the limiting factors. However, the baseline adaptations may be similar in the general population, but the exact changes are specific to each individual. And this overall slide here is related to exercise and fat metabolism. This is a simple look at how exercise can influence metabolism and sourcing of energy, pointing to how important exercise is and how a ketogenic diet could potentially accommodate such a shift in metabolism. Although there is a decreased reliance on carbohydrates, there is still justifiable need for them. It is likely that certain types of exercise intensity will ultimately determine the type of macronutrient best suited for this scenario. So what's more important, exercise or diet? Both are very important. As you increase exercise training and calorie restriction, this leads to increased augmentation and expression of regulatory proteins within skeletal muscle, which leads to increased intramuscular fat storage. Recall that a ketogenic diet mimics calorie restriction or limited food availability, so in theory a ketogenic diet could have the same effect. And so this may act as a defense mechanism during times of low glycogen stores seen with calorie restriction, or a KD. And this may provide increased capacity for fat utilization during exercise in trained individuals. Now, regardless of a person's metabolic abilities or muscle fiber types, the fundamental changes we have just covered will occur with such dietary changes and exercise. I know, this seems to be out of the blue, but just as I was speaking about differences in muscle fiber type and distribution and metabolic characteristics, there seem to be alternatives to a ketogenic diet that work well. It seems like we are right back to the point where we started the discussion of human performance. This goes to show that high carbohydrate diets are common and seemingly important, but recall the genetic variations. They may be related to regional and/or cultural dieting patterns. Looking to the evolution of the human diet says a lot about variability and how different diets can accomplish nearly identical tasks. Ultimately, genotyping may be the future of diet and exercise recommendations, as this biotechnology could determine variability regarding muscle fiber type ratios, metabolic function and capabilities, and cardiorespiratory capacity. Because of such variability, perhaps this is why many studies have concluded that there are no performance advantages of high-fat diets. So what are these studies saying? Well, pre-performance high-fat meals have no effect on performance. Well, if the body is not geared for using fats as its primary fuel source, then pre-performance consumption of fatty meals would most likely have no effect or even be a detriment to performance. Short-term high-fat diets decrease or have no effect on exercise performance compared to high-carbohydrate diets. Short-term ketogenic diets, as we have discussed earlier in the presentation, do not allow the body to fully adapt to the changes in metabolism of nitrogen, carbohydrates, and fat. So it makes sense that short-term high-fat diets would be detrimental to performance. Moderate-term high-fat diets have the same effect as high-carbohydrate diets. The moderate-term high-fat diet seems to coincide with the timetable for keto adaptation, and so it makes perfect sense that a ketogenic diet would grant effects similar to a high-carbohydrate diet. Long-term high-carbohydrate diets are better for endurance performance than high-fat diets. Well, a long-term high-fat ketogenic diet would likely be outperformed by high-carbohydrate diets due to a lack of adequate protein provision and optimization of important elemental ions, such as sodium and potassium. These factors may not have been a part of the intervention in these studies. So what about those ultramarathon runners? So ultramarathons are essentially prolonged intense exercise, usually greater than 26 miles, that result in ketosis due to depleted glycogen stores and increased oxidation of free fatty acids. If this type of event induces ketosis, then it seems logical that implementing a ketogenic diet would help establish a normalcy geared for using ketone bodies as energy. And even during the ultramarathons, the moderate and high carbohydrate consumers also produce ketones at different levels and times during the race. This point underscores the inter-individual metabolic variability that has become such a common theme in this presentation. Tim Olson is an ultramarathon runner, and he broke a 100-mile course record by 21 minutes. Obviously, Tim's muscle fiber type distribution and metabolic characteristics, along with his physical makeup for running, likely fit well with the ketogenic diet and his training protocol. He was on a KD for 1 year, and he attributes this success to diminished need for caloric intake during the race due to increased fat metabolic efficiency and glycogen sparing. But just realize, not everyone is going to be able to be a Kenyan long distance runner on a high carbohydrate diet or an ultramarathon runner on a ketogenic diet. So there's got to be a compromise, right? Well, there is some middle ground, and high fat intake, roughly 60 to 80% of calories, for 5 to 6 days, and carbohydrate loading, 70 to 80% of calories, for 2 days, has been shown to increase fat oxidation rates and spare muscle glycogen during submaximal 65% VO2 max exercise, more so than a high carbohydrate diet. This level of intensity fits quite nicely with cardiovascular health and fitness. Also, with a couple carbohydrate loading days every week, the overall diet may be more palatable, which helps increase dieter compliance. And exercise tolerance should be relatively preserved regardless of metabolic variability. The cyclical KD may be most beneficial for those trying to maximize their intermediate intensity goals, like long distance running and cycling. And so this modified KD, in my opinion, may apply best to the general population because it's very similar to the popular paleo diet. And the targeted KD may benefit powerlifters and other athletes that require more anaerobic energy for high intensity explosive events. Now, bodybuilders, they kind of fit in with cyclical and targeted at the same rate. Possibly a cyclical KD could be implemented, but the targeted could also be implemented, but instead of taking carbohydrates before workouts, maybe just after. After all of this, in my opinion, since humans have evolved to consume foods with varying degrees of macronutrients for energy production, it seems logical to recommend a diet that is associated with decreased risk of disease and increased exercise performance. But can a ketogenic diet cover all nutritional bases? And that's what is to come in the next part, nutritional strategies.